Welcome, students. In this video, we are going to study introduction to techniques of differentiation. Basically, we'll go over some basic rules that are going to help us calculate derivatives. First theorem is for derivative of a constant function. So we have here the derivative of a constant function is equal to 0. That is, if c is any real number, then derivative of it is 0. We can see that by looking at the graph of constant function, y is equal to c, then if we look at the slope of tangent line at any point of this straight line, then we see that it is going to be parallel to x-axis, meaning that its slope going to be equal to 0. We can also show this by using a limit definition of a derivative. So our function f of x is equal to c. So f prime of x is equal to limit when h is approaching to 0. Our function at point x plus h is equal to c anyway, minus f of x, which is c, divided by h. So that is 0. Next, power rule. If n is a positive integer, then derivative of x to the power of n with respect to x is equal to n multiplied by x to the power of n minus 1. Let's prove this one. Limit when h is approaching to 0 of, so we have f of x is equal to x to the power of n. Limit when h is approaching to 0 of f of x plus h. So this is x plus h to the power of n minus f of x, which is x to the power of n divided by h. Let's calculate the value of that limit. This is equal to limit when h is approaching to 0. Let's use binomial expansion to open up brackets here. So we'll have x to the power of n plus n choose 1 multiplied by x to the power of n minus 1. This is going to be n multiplied by x to the power of n minus 1 multiplied by h plus n choose 2. This is going to be equal to n factorial divided by 2 factorial divided by n minus 2 factorial multiplied by x to the power of n minus 2 multiplied by h squared and so on. And the last term is going to be h to the power of n minus, we have this x to the power of n divided by h. So these two terms are going to cancel out. Then let's see what's going to be left. Limit when h is approaching to 0. So if let's pay closer attention to this term here. So h is going to cancel out. So we'll end up with n, x to the power of n minus 1, and plus this huge expression of other left terms. Now, if you pay closer attention, we can see that when we cancel their h with an h in denominator, all these terms here are going to have a factor of h to some power. And when we take their limit, when h is approaching to 0, so we'll have some expression here that is invariant of h multiplied by a factor of h to some power. So all these terms are going to disappear when h is approaching to 0. So basically, we'll have limit, or when h is approaching to 0 of that n x to the power of n minus 1 that doesn't contain h, and plus bunch of zeros. So this is equal to n x to the power of n minus 1. Okay, next rule, extended power rule. If r is any real number, so this is similar to this one. However, in that case we had positive integer. However, that is going to work for any real number. So derivative of x to the power of r with respect to x is equal to r multiplied by x to the power of r minus 1. Okay, next rule, constant multiple rule. If f is differentiable at x and c is any real number, then c multiplied by f is also differentiable at x. So basically, we can move constant out of that derivative operator. You can see why this is true by again showing it using showing that proof using limit definition of derivative. All right. Sum and difference rule. If f and g are differentiable at x, then so f plus j and f minus j. And we can use the following rule. So we can use distributive rule for the sum. So basically, if we have derivative of a sum, it can be expressed as a sum of derivatives. Let's show that. Let's show proof for this statement here, and for a second, it's similar. Limit as h is approaching to 0. So our first function is going to be, let's call that some function h of x, which is defined as a sum of function f of x plus g of x. Let's use different letter. In fact, instead of h, let's use some a. L of x, then L of x plus h is defined as f of x plus h plus g x plus h minus L at point x, which is defined as f of x plus g of x divided by h. We need to find that limit here. Then let's group these terms up as follows. So f of x plus h minus f of x divided by h multiplied by limit, which is approaching to 0, g of x plus h minus g of x divided by h. So we can split this limit of a product into product of limits, since in fact, guys, here should be sum of product. So we can split the limit of a sum into the sum of the following limits, since these limits, they exist from our statement of theorem. So f and g should be differentiable, meaning that these limits should exist. So this defines derivative of f then, and that defines derivative of g of x. Basically, derivative of the sum of two functions, of two differentiable functions, is defined as the sum of their derivatives. Okay. Now, higher derivatives, we can differentiate our function several times as long as its derivative exists. So here is a notation for nth derivative of y, or f of x, nth derivative of f of x. So here are several notations for higher derivatives. And this is, here we use the following notation for nth derivative of f at point x. Now, guys, we are going to use the following rules to solve a bunch of problems in our next video, where we are going to solve problem sheet on section 2.3. Thanks for watching.